Mic check. Mic check. Check, check, check. Sounds good? Okay. All right, thanks. Okay. I'll try to keep the Slack conversation open, so if there's any questions, I'll try to answer them from the Slack as I'm doing this. All right. Okay. My name's Nick Carey. I'm a grad student here at Hopkins in the computer science department. I work with Tomas Pidavari, David Elbert you saw yesterday, and the eScience group under Alex. Today I'm talking about my EEG research in P300 waves and rapid serial visual presentation. But mainly I want to use that as an introduction to SciServer and how I've used SciServer for my research and how I found it incredibly useful for everyday prototyping of your ideas, working with big data, and collaborating with other people. And to really emphasize the collaboration part. So I have a signal classifier demo that I'll get to later that if you guys would like to run alongside me and try out some of the SciServer features, this code's available for you guys to run alongside me. The prerequisites for that is that you need to be a member of the IDIES Hackathon 2019 group. I think most of you are already part of that group. If not, we can sort that out right now. I'll bring up the group membership page, and if anyone's not a member, we can get them in there. And to also clone the Hackathon GitHub. Some of my code is in the demo section of that repository. URL's up here. URL's also right there. I'll bring that back up if anyone hasn't seen that yet. I'm going to switch over to SciServer groups page real quick just to ensure that everyone who wants to follow along is in the group. If you don't have a SciServer account, it's free. I highly recommend it. In the dashboard, sorry, I went a little quickly there. There's a Groups tab on the dashboard. Inside of it, you should see the IDIES Hackathon 2019 group. Its members. I know Jordan was sharing some data through the Baltimore shared files. So many of you probably are already in it. If you're not, put something up on the Slack. I'll send you an invite. Okay. So once you're in the IDIES group, if you click on the compute page, you can create a container here. So before I get into some context, I'd like to just start you guys off on the SciServer page so that we can get these notebooks running while I'm talking. Because the one notebook that collects the EEG data from CashJobs takes a couple minutes to run. And instead of waiting around for that, we could start it now, and then once we get to it, after I talk for 5 minutes. So anyone following along, all you do is at the compute page, compute jobs, click on interactive notebooks up top, create a container. And we can just call this demo. And we can use the basic Python and R image to run this data preparation code. Annie, you got a question? Oh, just stretching. And stop me at any time for questions. I know I'm blowing through this a little quickly. So what the compute tool is it's essentially you spin up these containers, which are environments for running your Python code in. And the advantage of these environments is that it already has many of the common tools pre-installed. So, when I was doing my classes in computer science, the first few courses were always devoted to, setting up your coding environment, installing the packages you need, et cetera, et cetera. That's one of the great things about side servers. You don't really have to do that. It's already kind of set up for you. Clicking on the container that we just created, it brings you to kind of a file browser. You have your own storage area and carry. But what we're going to need is a terminal to interact with this. And oh yeah, storage is guaranteed to be there for a bit longer than temporary is. Yeah, it's backed up. Yeah. So I find a terminal to be pretty useful when working here. Again, it's a familiar bash terminal. Starts off in your home directory. If we go to the workspace directory, storage should be your username right there. Go into persistent. And this is where most of my files are. You won't see all this. But once you're in this persistent directory, that's where you want to clone the Visualization Hackathon repository. So we just do a quick git clone, and I'm going to cheat and copy and paste. Okay, well, I already cloned it, so, but this will work for you guys. Okay. So once you have that GitHub repository cloned, it'll show up in the file browser. And the code we're going to be running later is under demos, EEGNet, EEGNet data prep. Okay. Yeah, stop me at any time. Let me check the Slack real quick. Okay. So if you guys are following along, there's one requirement for this notebook to run, and it's in the comments at the top of the notebook. It's just a visualization library that I'm using. You can just copy that and paste it into the terminal, and that should install. Once that library is installed, which is going to take a second. Once the library is installed, restart the kernel on the notebook, and then run the first 3 cells, or first 4 cells of the notebook. And we'll come back to this later. So back to context. Why am I having you do all this? So let's start the presentation back. Okay. So I'd like to show this EEGNet signal classifier demo as kind of like a SciServer tutorial, or a demonstration of what SciServer is capable of in a collaborative way. So by the way, whenever I mention EEGNet, that's work done by Army Research Labs Center for Adaptive Soldier Technologies. They've developed a neural network for classifying EEG signal. I've been using their work. I've worked with them up in Aberdeen. They know what they're doing. And they've written a very compact convolutional neural network for classifying EEG signals. Compact meaning it's really easy to run, it's quick to run, you can run it in real time. And that's what my demo is we're going to be running that neural network. But we'll come back to that. So my research is in data exploration. I'm working on new ways to interact with data, play with data, render it, and give feedback on data renderings. And there's really three pillars to this. There's the machine learning for finding trends, visualizing those trends, and then interacting with those trends. And bringing them all together is what I'm interested in a system that kind of speeds up this loop of finding trends in your data and interacting with them. It's currently slow iteration. You spend some time making a chart or a graph, evaluate it. If it's interesting, you continue working on it. What I want to do is kind of speed that up. Anything that's not interesting, I want to discard quickly. Anything that does catch my eye, any data renderings that do catch my eye, I want to explore more without having to write code for every data rendering I come across. And to this end, I want to create an immersive environment to engage with this data. Mapping data to your natural senses and then reading your reaction to that data is what I'm trying to do. And a tool to do that is EEG signal processing. So I have a EEG cap that you wear on your head, and what this is basically electrodes that you place along your scalp, and these electrodes read microvolts that are running along your scalp. And these microvolts, your brain's response to things that it sees, there are standard responses that have been researched by neuroscientists. One such response is the P300 response. They call this the oddball response. Whenever you see something that catches your eye, see something that interests you or surprises you, your brain gives off a P300 wave. And that looks like this, if this video works. So this is kind of some example, or just example EEG data, these microvolts along your scalp. When the user sees something at time 7, you get a negative deflection in the signal and then a strong positive deflection. And this is within the EEG data. So this might sound like science fiction, but it works. I'll demonstrate it to you. This is rapid serial visual presentation. It's when you show images very quickly to somebody and you're able to elicit a subliminal P300 response when someone sees something that interests them. So you might think that 10 images per second, that's too quick to pick out anything meaningful, but it's not. I'm going to play this video once again and ask you guys to look for the stop sign. Let me know if you can pick out the stop sign from the computer monitor that's in the video. Yeah? Could you guys find it? There you go. So it's a subliminal response, but it evolves into a conscious response as well. Like we were looking for the stop sign, and we consciously saw it. I don't know if the refresh rate on this projector is fast enough to show the stop sign in every frame, but it's there. So this is what your EEG signal kind of looks like as it's running in real time. Yeah.
When you're looking for, with that rapid set of images,
Mm-hmm.
someone's response with that P300, is it that they've already been exposed to all the images and that's slow capture to know, like, oh, this one's interesting to me, so then, like, these spin rapidly, it's interesting again?
Yeah. So it's context dependent. Like I told you guys to look for the stop sign, and you were telling your brain to be interested in the stop sign. And then when you saw it, you gave off a P300 because you recognized it. And yeah, that's in real time. So it's called the P300 because the wave happens 300 milliseconds after the event that elicited it. And P is for positive because you get a positive deflection in the EEG signal. Does that answer your question?
Kind of. So, like, that person seeing how that P300 when there was someone sitting kind of with their arms on their knees, is that because, like, they've been told look for that and that is similar to us in the stop sign? Or is
Yeah.
it, like, in that rapid flash, that was actually what interested them?
A combination of both. You can't help what interests you. You see something. If you see like one of those pictures, I think there's a man holding a gun or something, and that's that's going to naturally interest you because it's dangerous, right? So you're probably going to give off a P300 for that, even if you weren't told to look for it. But you can also prime the user to look for something specific and force them to be interested in it. So that's how I'm using, go ahead.
How many channels is the EEG?
Oh, okay. So in this example, there's only one channel shown. I'm going to show some more data in the next slide. This is some reading from a 32-channel cap. A lot of the professional caps are 64 electrodes. It even goes up to like 128 electrodes. The cap I've used in practice is a 16-electrode cap, just because it's a huge pain putting on the cap and taking it off, because you got to put gel in your hair, you got to put the electrodes in the right spot. The data that we're working with today is 16-channel EEG signal.
I'm asking this because of your question, because depending on the picture, you can simulate different areas of the cortex. So if you have more channels, the capacity to, the resolution of the detect the area that was simulated is higher than if you have a few channels. Can you repeat all the questions?
Okay. Oh, okay. The first question, if I understood it correctly, was in regards to the context of eliciting a P300 wave, when people naturally give off a P300 when they just naturally are interested in something versus when they're primed to be interested in a particular subject. The second question was about how many channels are in the EEG signal, and the resolution that gives you more channels, you have more information about what's going on.
About the areas that are simulated with the pictures that are happening.
Okay, so like the areas of the head that are stimulated? Yeah.
You have different areas of the
Mm-hmm,
cortex,
mm-hmm.
and depending on the picture, you have the area is simulated or not, depends on.
Yeah, absolutely. In this example, the top channels up here are more towards the front of your head. These bottom channels generally are more towards the back of your head. And generally speaking, P300s originate from the back of your head and kind of propagate towards the front. So in this snapshot of EEG signal, these peaks up here, these are actually just eye blinks, which show up a lot more in the front of your head than in the back. These eye blinks are generally considered noise and artifacts I would want to get rid of, because it's just me blinking my eyes. If I was clenching my jaw, that would show up more in the back of the head as an artifact. I don't think I clenched my jaw at all in this example, but yeah, the signals originate from different places in the head. P300s generally are stronger exhibited towards the back of the head. Okay, so to recap, rapid serial visual presentation is a paradigm that's designed to stimulate P300 responses. P300s are given as a reaction to oddball events, but you can also prime a subject to be interested in a particular thing. And I'll get to an example shortly. Oh, cool, yeah. And when presented with up to 10 images per second, users can reliably pick out targets versus distractors. And I'm going to keep using this targets versus distractors vocabulary. Targets means images that I'd like the subject to trigger on or give off a P300 for. Distractors are images that aren't supposed to be interesting. Yeah, I will post those in Slack afterwards. Okay. So how do you use this for data exploration? The problem space assumption here is that an algorithm can't necessarily identify images that we would find interesting, whereas a person, a user, can. This is quickly becoming untrue with the advances in image processing and neural networks used for object detection in images and object identification in images, but I think there's still some time left for humans to be in the loop. And what we're going to be looking at in the demo, in the code demo, is this EEG classifier part. Users are looking at images, and the neural network classifier is looking at the EEG signal and deciding whether a given chunk of signal had a P300 in it or did not. And this leads to the human-machine co-learning idea, which is what I'm developing. The computer presents the user with ideas. The user selects ideas. The machine presents users with similar ideas, and you repeat and you repeat. And this can be used to do a data set search, sorting images, et cetera, et cetera. So again, RSVP is used to quickly gauge what the users are interested in, and new sets of images are generated based on user interest. So to illustrate this with an example, I've come up with just a toy data set where I've taken a 3D cube, 3D wireframe cube. I've rotated it with a bunch of noise to create just like a noisy field of points. And then I'll apply more subsequent rotations to either generate some of the cubic structure, the original structure, or in most common cases, just noise. So for this toy example, I'm flashing images to the user, and I ask them to look for structure in the images. And most images are going to show just noise. But some of those images are going to be rotations that are close to the original rotation used to hide the cube, and will show some of this cubic structure. So as users trigger on images that show some of that structure, we will then explore similar rotations used to generate the cube structure and hopefully narrow down on that original cube. So we're using the RSVP as like a steering function. This is to say hot or cold. This image is a bad rotation. This one actually has some cubic structure in it. So again, you're going to have most images are going to look noisy like this, but then some will show some cube structure here, some there. I prime them to say look for any sort of organization or structure in the noise. So they discover the cube as they go on. And that's part of the challenge is as you're narrowing down on the structure, the user has to kind of discriminate between more and less structure. And that's kind of what we're exploring is in real time, how can a user kind of refine their idea of what a target is versus a distractor. And since this is a visualization hackathon, I thought I'd mention that context is really important for your visualizations, right? In RSVP, we're looking at these visualizations at 10 per second, right? And a simple scatter plot is going to create artifact reactions that you might not necessarily want, as opposed to like a low-resolution 2D histogram. And that's what we found when we were first running this experiment. I originally visualized this cube structure as just a regular scatter plot. But what I found is that when showing these at 10 per second, it kind of created an unintended animation effect. It kind of looked like these points were like crawling around, and it generated reactions that you weren't necessarily looking for. You'd be responding more to the animation between the frames than the actual frames themselves. So I found that in this context, kind of lowering the resolution into like a 2D histogram made it more easily digestible quickly and created less of like an animation effect. So yeah, different visualizations are important for different contexts, et cetera. You guys know that? Okay. Sorry?
There are more points in the pixel, like a brighter.
Yeah. So it's a 2D histogram. Sorry? Oh, okay. He was asking how the picture on the left was generated, right? And this is a 2D histogram. So, if there's 5 points within this box in the original, then, that pixel's brighter. So, yeah, pixel intensity is how many points are within that box. Okay. So there's a lot of system engineering challenges when it comes to working with RSVP. And this is going to lead me towards SciServer here. But P300s are not consistent waveforms. Like this is an example of like a raw EEG signal P300. I know it's P300 because the event happens at time 0. We have a slight negative deflection here, and then a positive spike about 300 milliseconds after the event. But this is what the raw data looks like, and it's not easy to really, look at that and immediately say, oh yeah, that's what a P300 looks like. And that's because there's a lot of noise in the EEG signal. I mean, we're picking up microvolts along your scalp. There's a lot of interference. You get interference from power lines, from lights, from your computer, if you're not properly grounded. So there's a very low signal-to-noise ratio. But that's where our classifier comes in. More challenges is you're kind of stylistically challenged wearing this cap. That's me. Here's some more examples of EEG signal. This is some cleaned up signal, and you can generate this in the demo notebook that we're going to run in a minute. The top part is a plot, not the best visualization I know, but this is a plot of 16 channels, and this is a P300 response, versus on the bottom, this is a distractor response. So this is a non-P300 response. And so our task for our classifier is to be able to differentiate between target responses and non-target responses. So the scaling on these two graphs was a little different, but you'll kind of notice that there's, in both graphs, we have a spike at about 0.1 seconds after the event, after a picture was shown, for both distractors and targets. This is actually called P100 wave, and that's a standard response to anything flashing in your face. Whether you're interested or not, if something flashes you in the face, you give off a P100. And we can use this just to see if someone's paying attention or not. So if you're not looking at the screen and there's RSVP going on, you won't be giving off those P100 responses. If you are, you'll always see a slight spike in the EEG signal about 100 milliseconds after the event. So what makes this a P300 is we see a negative deflection about 300 milliseconds afterwards, followed by a strong positive spike. So this looks noisy, right? But this is actually pretty cleaned up in terms of EEG signal. I mean, I'm sure there's more I could do for it, but this is actually the average of 32 target responses. So from 32 times that I was supposed to be giving off a P300 signal, this is the average of all those 32 responses. And this is the average of about like 400 distractor responses. So by averaging responses together, we can kind of get rid of the noise and see what's constant in all of those responses. Okay, so what we're going to be running today is EEGNet. This is something developed out of ARL. It's brand new. I mean, they just published this paper this summer. Their paper's available at this link, and the code for their EEGNet is available at their GitHub that they've published. It's also going to be in the demo code that we're going to be working with today. So now I'm going to turn to SciServer and kind of show you guys some of the tools available there that have helped me run these classifiers. Okay. All right, so I'm going to start with CashJobs. So CashJobs is a SQL Server database, and everyone who has a SciServer account has access to it and can play with it. If you need more, this is, for everyday data analysis stuff, you don't necessarily need to be putting your data into a database, but I found that it's a very safe place to keep my recordings, and it also makes data aggregations a lot easier. So if you're at the query page, you can kind of do some quick queries to see what your data looks like. So I've put, yeah, I forgot a from. Thanks, Ani. So not only that, but you can publish your data sets for other people to look at as well. And that's what I've done with some of my recordings, is I've put them in public tables. So for example, running a quick query.
So CashJobs has its own groups right now, believe it or not. In the next version, we're trying to integrate CashJobs groups with the SciServer groups.
Okay.
But right now, it's own groups.
But I believe anybody with an account can look at tables that you've published to the public domain. Yeah. So So if you guys are on CashJobs, you can run this query yourself and see some of the metadata I have from my recordings. This table, the sessions table, is really just metadata for some of my recordings. To actually look at the raw EEG, let me see, I think that'll work. Review sessions. Typo, my bad. So this is what the raw EEG data looks like. Pretty simple. It's just a timestamp with microvolt readouts from each of the electrodes. It's about as raw as it gets. So moving on from CashJobs, you can interact with, sorry, go ahead. Okay, so what I'm going to be using the classifier to predict is whether a epoch of code, epoch of EEG signal, about a second's worth of EEG signal, has a P300 response in it or does not. So it's a binary classifier, whether it's a P300 or not, basically. And I'll show you the code that does that now. Okay, so in the Visualization Hackathon GitHub, demos EEGNet, we can go to EEGNet data prep. So what I'm going to do is prepare some data for the classifier, and then we're going to run a GPU jobs to actually run the classifier and train it. GPU jobs is brand new. We just got this working this week, so we're on the cutting edge here, and if you guys would be happy to test it with me and see if anything breaks. All right, so earlier I had you guys install this MNE library with the pip install, if you guys are following along. Okay. This is just a wrapper for the data I extract from CashJobs. So what's cool about this is you can query CashJobs from within these interactive notebooks. And it's very easy too. Oops, yeah, I need to install that. Okay, if you did that git install or pip install MNE and it's still giving you this no module named MNE, all you gotta do is restart the kernel. So now it should pick it up. This start here means it's executing. Okay, yeah. So it picked it up. So all you gotta do is from server import CashJobs, and from there you can write your queries as strings in Python, and it's as simple as cashjobs.execute query, and you get a data frame, a pandas data frame as an output. So I don't want to subject you to my terrible SQL here, but essentially what this class is a wrapper for that raw signal that we saw in CashJobs. Okay. So this is the cell that's going to take a couple minutes because it's querying all the sessions from CashJobs. Actually, I'm going to cancel it and only query a couple sessions just to make it go faster. Yeah, interrupts.
So it takes time, but it's still running in interactive like quick mode or faster?
Sorry?
You're saying it's going to take time, but you're running the query in quick mode in CashJobs?
Yeah, yeah. The reason it's taking time is I wrote some code in here to match up the event signals with the EEG data, and it's not as efficient as it could be. I mean, it's a hackathon after all, right? But I mean, when I say it takes time, it takes like 2 minutes.
Because otherwise it might not.
Oh, Oh, yeah, this is a collection of like about 20 queries. For each session, I'm querying it. So they're quick queries, relatively. But since I'm running about 20 of them, it adds up. So what I'm doing here is I'm extracting data from different recording sessions that I've placed on CashJobs. So I've recorded about 20 3-minute sessions with the EEG cap. And this code is essentially grabbing that raw EEG data and matching up the stimulation times with the EEG signal. Because you need to know exactly when the image was presented to the user in order to find the P300 signal. So like I said earlier, it happens 300 milliseconds after the event happened, et cetera. Okay. So, okay, go ahead. There is. That's actually an important. So he was asking if there is a delay between the signal capture and the image presentation while I'm running the experiment. And there is. There's a few libraries that I use to do network time protocol to match up the time signatures between my recording PC and the presentation PC. Yeah, timing is very important when you're doing EEG signal analysis because, again, without context, the signal's useless, essentially. You need to know what the subject was looking at what time when you're looking at the EEG signal. And that's essentially what this code is doing, is matching up the times when the subject was presented with an image with the subject's EEG signal. Yeah. So I can confidently say, there's no more than like 2 milliseconds mismatch between the image presentation and the EEG signal. And 2 milliseconds isn't going to make too much of a difference when we're looking at stuff that's on the order of like hundreds of milliseconds. Of course, if this was like a medical procedure or something, then yeah, I'd need to be a bit more precise, but Okay. Yeah. So the question was, sometimes when you're doing a recording with an EEG cap on, you have your eyes closed and you just might not see an image that was presented because you had to blink, because you had to wipe your eyes. And yes, that's absolutely true. Not all target images that are designed to elicit a P300 response actually do elicit a P300 response. Sometimes, like you said, I'm just not paying attention. I'm tired. Like doing these RSVP sessions is exhausting because you got to stare at a computer screen for 3 minutes at a time and not blink and pay attention to every single. It's not the perfect paradigm at all. So you kind of just have to accept that a lot of your responses that are supposed to be target responses aren't necessarily going to even have a P300 in them just because I was too tired to give one off. There's also an exhaustion period with P300s. Right after you give off a P300, you're not going to be able to give off another one for another few seconds. You can't just be interested in things like one after the other, like that. So when we're designing our training sets, we make sure that our target images are not back-to-back. But it is an imprecise, it is imprecise. Not 100% of the time you're going to be interested in what you're supposed to be interested in, and not 100% of the time we're going to be able to pick up those P300s. But it's an accuracy we live with because it's part of the science. Yeah, exactly. All right, so after loading some of this data from CashJobs, I can visualize it here. So let's look at session 4. So again, this is some more raw data. What this is it's an average of all of the target responses from session 4. I know session 4 is meaningless. It's just a 3-minute session that I had recorded. So this is an average of like 32 responses that are supposed to be P300 waves. And again, this is to show that you know, this is hard to pick up, right? Like you kind of see a negative deflection here about like 0.3 seconds and then a positive spike at 0.4. But really this is to illustrate how noisy this data is, you know, how many artifacts there are in it that you're not necessarily interested in. And I really show you this to show you the power of these neural net classifiers and how good they are at you know, differentiating between this and this. This is the average of the distractor responses. So this is essentially what we're asking our neural network to differentiate between is this distractor response and this target response. And again, these are going to look slightly different just because this is an average of 400 responses, whereas this is an average of 30 responses. So you know, you get a little bit less noise in the distractor response signal. But our classifier isn't looking at the average of, you know, 400 responses. They're looking at one response at a time. Okay, so this block of code saves those saves the arrays that I've created to a file so that the GPU jobs can read the data and learn off of it. All right, so how do we run a GPU job? Well, from the dashboard, we can click on Compute Jobs. And before we actually run one of these jobs, I'll show you the code that we're running, and that is EEGNet job. What this block of code essentially is a wrapper where I've wrapped the ARL's EEGNet into a class just so I can run it on the GPU and load my training data into it. I've got an evaluation method that, okay, so what we're passing to this class is training data and evaluation data. So when you're working with neural networks, it's incredibly important to really evaluate how well your classifier does. You know, there's a lot of things you can tweak with the networks, you know, in terms of like training iterations, in terms of class weights, et cetera, et cetera. So you need a good way of testing whether these changes you make to your classifier are really improving its performance or not. So I'm passing training data and evaluation data, right? Back in the data prep stage, the save to file function takes a number of sessions to use as training data and a number of sessions to use as evaluation data. So I'm basically pretending that, well, I'm not pretending. I'm not training the classifier on a subset of my data so that I can use that data to evaluate how well the classifier works. You don't want to evaluate your classifier on your training data because one of the problems with neural networks is that they tend to overfit their training data if you train it for too long, so that it will only recognize data that looks exactly like the training data and not, you know, generalized to other data sets. Go ahead. So a session is a recording. No. I only combined those together just so we could see what it looks like. Because, here, I'll show you. If I just looked at one instance, I think that's what this one will do. Yes. So he said technically we're classifying an individual wave and not the average of the waves, which is true. I only averaged the waves together just so that we could see what it looks like. If I just show you one individual wave, which I'm doing right here, yeah. Again, not the best visualization, but yeah, like there's not much we can really tell from this with the human eye, right? This is a target response. Each of the channels, these are 16 channels. Yeah, really I couldn't tell you from looking at this whether it's a target or a distractor response. I mean, I know it's a target response because I got it labeled target 02, but it's much harder for us to decipher, you know, a non-average. Sorry, go ahead.
So you are using a convolutional neural network,
Mm-hmm.
and there are some discussion about the use of convolutional neural network in other contexts besides the images,
Mm-hmm.
because during the process you input some information about the data source.
Mm-hmm.
So I imagine that you pass with a determined window to the convolutional, and it is trying to detect the pattern, and to see if the pattern is equal that you have stored before. Is that what you do?
Yeah, yeah. In,
I might repeat this question.
yeah.
Fine.
So the question was, am I losing?
Oh, why did you choose to work with convolutional?
Okay.
Because the issue is that they lose some aspect of the data
Mm-hmm.
that is useful to analyze the image, but it's not useful to analyze different types of data.
Okay.
And the mechanism that you use is to the input of the convolutional neural network. Because you have a vector of numbers that
Yeah.
represents the signal.
Mm-hmm.
So the input is the vector.
Yeah. Yeah. So the input for the network is 1 second's worth of 16 channels of EEG data. And so 1 second's worth is about 128 samples. Because we're recording at roughly 512 hertz, 512 readings per second. I've downsampled that to about 128 readings per second, just to make it easier for the net to run on, and to lower the amount of parameters in the net. But as for why this works, the ARL guys explain it really well in their paper. I couldn't quite hope to match that, but here, let's take a look. So yeah, this is a convolutional neural network, and without going too much into how it works, their results don't lie. You know, they've achieved accuracy with this net that hasn't really been seen before, and not only that, it's compact and pretty easy to run. It's quick to run.
So plotting the signals
Yeah.
using a neural network to classify the plot perform better than classifying the actual signal as a summary dashboard.
Oh, okay. I'm not passing the plot of the signals to passing the resampled data to the network. I was only plotting this just to show you what it looks like. Yeah, yeah. So back at the data prep stage, in this class, it's really just writing down a file of arrays. Yeah, the model's not taking in an actual plot. It's just taking in an array of, yeah, of the raw signal. Yeah. Exactly. Yeah, remember this stuff. I mean, it's not exactly this stuff because I've done some cleaning to it and some normalization, but essentially the classifier is being run on these raw readouts.
Oh, but not the convolution. My question is about the transmitting neural network that the convolutional is applied in this. I have used it in the text, the natural language,
Mm-hmm.
but it has been used a lot in image processing, not in other contexts.
Yeah, so it is new for them to be applying convolutional neural networks to EEG signal. And I can't quite, off the top of my head, tell you the rationalization for it.
But I you said it worked.
Yeah, yeah. Again, I was more trying to gear towards how to run this stuff on SciServer than explaining, you know, their choices for how they constructed their net. I'd be happy to, you know, point you towards their paper and show you their rationale for it. But didn't quite prepare that for today. So we have our GPU job. This is what we're going to be passing towards the SciServer GPU jobs queue. I'd love to run this interactively, but at the moment, since this is such a new feature, we have to run it in the jobs queue. Now, how do we do that? So from the SciServer jobs queue, we can select GPU small jobs, because this should run pretty quickly. TensorFlow compute image, because we're using Keras and TensorFlow libraries. You give it access to some of your folders, et cetera, et cetera. And you select the notebook you want to run. Whoops. Okay. So this should take about a minute or two to run. And what it's going to do is it's going to train on let me bring this up. So when I created the training arrays, it's going to train on sessions 2 through 18 and then evaluate on session 19. So that's as if I recorded, a bunch of sessions to train this model, and then later on I sat down and used the learner to classify previously unseen data. Mm-hmm. Yeah. Yes. So this EEGNet job is what I'm running through compute jobs. So compute jobs is a little bit different than compute interactive in that it starts up a brand new container for the job. So if you got to install some libraries on that container before you run the job, you need to include that code in your job. So that's what these first two cells are kind of doing, is just configuring the environment a little bit to run EEGNet. Specifically, there's some Keras configurations that I just have to spit out to a configuration file. So there's no transfer learning in this example. I'm starting with a fresh model, just training on 18 of my sessions, and then evaluating on one of them. A lot of what you want to do, there's cross-validation. And if I was coding up a cross-validation for this model, I'd want to kind of use I'd want to train on every model or every session except for one, and then evaluate on that session for every session.
So this is not the net that has been trained by
No. Well, it is their net. They haven't trained it. I'm training it on my data. So I've essentially taken their network and run it on my data as an evaluation. Oh, okay, yeah. So, yeah, I'll show you that. Yeah, that's right here. So let me show you the directory structure real quick. In my EEGNet folder, I have their ARL EEG models. And you get this folder from just cloning their repository. I think there's a link in the presentation. Here, I'll bring it up. Yeah, I mean, I'm not using any of their data to train or their network, but hold on, I was just there. Yeah, so this is their repository. So importing, again, their code for this is incredibly short. This is their entire network, EEGNet. Most of it's a comment, but they make their network in about 10 lines of code right here, or maybe 20. And again, the explanation for their network is better read in their paper than me trying to bumble through it. But So how I import that in EEGNet job is I have that folder that I've cloned from their repository in the working directory of this notebook. And yeah, it's as easy as that, as import module. I had to use this import lib library because they have a hyphen in their name, and default Python doesn't like that. But in terms of running their model, it's these two lines of code. So I construct their model, say there's two classes I'm looking for, with P300 or without P300. 16 channels, 128 samples per input epoch. Okay, so I compile their model, and then up here, once I get the input data, this is it. You fit their model here. Provide training data, provide training classes, number of times to iterate over the training data set. And then when I'm evaluating it, I use model.predict. And I provide a block of data to predict what class that block of data belongs to. Incidents, like how many there are in the data. Okay, yeah. So that's another problem with using this, is that because I can't elicit P300s back to back, there's roughly 8 distractors per one P300, roughly. So I mean, you saw in the earlier sessions I had like 30 examples of target responses and like 400 examples of distractor responses. So there's a big imbalance between targets and distractors in these data sets, which I've tried playing with class weights to weight the target classes a bit heavier. Yeah. Yeah. Getting to that. The output for my evaluation is very basic, just true positives, true negatives, false positives, false negatives. So let's see if it's done. It should be done. I'll refresh this. Yeah, completed pretty quickly. June 26, yep. Okay, so the jobs queue will spit out its output into your persistent working directory. There's a jobs folder. I can't read this, but 2019. Yeah, so the latest one is 2.6, yeah. Okay. So first we'll look at the score file. So for this example, I did about 90 training iterations, so 90 iterations over the input data set. True positives, so that means true positives is when there is a P300 signal that was supposed to be present, and the classifier identified it as a P300. 29 of those, or 28 of those. True negatives is when it's a distractor and it classified it as a distractor. I got 365 of those for session 19. False positives is there's only one, so that's when it classified a distractor as having a P300. And false negatives, there's 6. So it missed 6 target responses that were supposed to have a P300 in them, but it classified those as distractor responses. Yeah. So these numbers are all right. I mean, obviously I'd hope to have 0 false negatives, because obviously. But I might have not even given off a P300 for those 6 responses, or I might have given off a P300 for one of where I wasn't supposed to, So it's imprecise. But what we really, like you said, what we really care about is picking up a P300 when there is one. So our true positives is the metric we really care about. We want that to be as high as possible. Yeah, so there were supposed to be 34 target responses in this session. I picked up 28 of them, which isn't bad. To look at the actual output of the classifier, so it looks like this kind of. So this is at the tail end of the file, so all of these are distractors. The true class is 0, 1. 0, 1 is the distractor class. And the prediction, it gives a decimal number of how sure it is that it belongs to that class. So okay, so what I'm going to do next is code this up to run it in real time as I'm making a recording, and it'll be able to spit out when I give off a P300 versus not. All right, well, thanks for, yep, question?
Can you plot the convolutional model in the site server environment? Because I have some thoughts in the Windows environment, I could not plot it.
Okay. So the question was, could I plot the
Convolutional neural network model.
the model? Could I plot the model? I haven't tried that. How would you do that in the first place?
There is a library in the Python to plot it, but it does not function in the Windows, so maybe the site server environment it can.
I haven't tried it. I'd assume that if it's anything like matplotlib or if it displays it as like a PNG or an image file, then it could absolutely be in a notebook. The actual neural network structure for this network in particular, it's pretty compact. There's only about 1,000 parameters. But even so, there's 1,000 parameters. That's hundreds of nodes. I don't know if I could fit that on a computer screen.
The other option is you are using the TensorFlow as a backend.
Okay.
TensorFlow has a library to describe all the data and the results. Maybe you can use those.
Yeah, yeah. He was suggesting I use TensorFlow to plot the network. And yeah, absolutely. I haven't looked into too much of the structure of the network itself, just because I'm using someone else's network. And most of that is included in their paper, which I can pull up the citation to real quick. All right, thanks. Thanks, Mupti.
Just to kind of help me understand sort of what's the application now that like you've been able to train to identify P300 within like that image set, can you then say like, okay, give someone any other image set,
Yeah.
and assuming it's similar types of people as what you trained on?
Yeah, yeah, no, absolutely. I want to use this with non-toy data sets. Like my hidden cube's really just like a prototype, just a demo. But this has absolutely is meant to be generalized to any image data set, really, where there's a difference between targets and distractors. But no, that's the challenge I'm facing now is how do I want to use this, What is exciting to me with the EEGNet that we just showed is that it's compact enough and lightweight enough that I might be able to run it on like a sliding window of EEG signal instead of having to have the EEG signal tied to specific events. Then I could be doing anything, like just browsing the internet on my computer and have this net running in real time on my EEG signal and see when I'm interested in literally anything that I'm doing on the computer. That'd be kind of cool as like a general purpose. Yep, go ahead.
Well, it can be very useful to analyze the body's response to stress to different types of stimulus, because in general we have a subject answer asking the user if they were influenced by the image or not, or by indirect stressful hormones on the blood. And here we have a direct measurement that the stimulus went to the cortex. So this is useful for
Oh, that's cool. Yeah. EEG's traditionally been used to diagnose a lot of medical conditions. For example, MS. A lot of people who are affected by MS have a different looking P100 wave. I mentioned that earlier, the P100 wave. This wave right here, that's kind of a response to seeing any sort of flash. People who are affected by MS typically have a lower amplitude P100 and a delayed P100, and doctors have traditionally used that to diagnose MS. These days, they've phased that out in favor of MRI-based techniques and spinal tap techniques. But yeah, absolutely. A lot of research in this area is being done by marketers. Obviously, they want to know what you're interested in. They want to know what ads speak to you or grab your attention. Who else does research on this stuff? I mean, I'd like to use it for data exploration. Like one other application I'm looking at is flipping through images of galaxies and classifying galaxies based off of, But to be completely honest, like running a neural network just on those images could probably do just as good of a job without having to have a human in the loop. So what I'm really trying to look for is areas that require human expertise in identifying something in the images and hooking them up to a headset, figuring out what's going on up there. Yeah. Okay. Thanks. I'll put the slides up on the Slack.